السلام عليكم.
عليكم السلام.
عليكم السلام.
Okay, we are done with the previous chapter, vapor power cycles. We are going to start a new chapter today. So let me share the screen. Okay, today we are going to consider what's in chapter 9, gas power cycles. In the previous chapter, we consider the same like this here. We have a hot body and we have a system and water. So this was what's called vapor power cycle. So this is a heat engine, and this heat engine will produce power. This is why we call it power cycle. So we are in the same range of talking about power cycles. The only difference in this chapter is that we are going to utilize gas. So the fluid is going through the system here will be gas, not vapor. In our previous part, regeneration reheat, it was vapor, and we used to have two-phase flow, either liquid and vapor, and we cannot apply the ideal gas assumptions. Now today we are going to start a new chapter where we talk about gas power cycle. Means that the fluid here is gas and not liquid, not mixture, but it is only in the vapor form. It is a gas, and this is why we call it gas power cycle. So we're going to talk about the cycles that produce power, and they are utilizing gas. And therefore we have here, similar to the previous part, we have W cycle is equal to Qn minus Q out, and the efficiency is equal to the work divided by Qn. What do we want to learn from that? Similar to the previous chapter, we are going to consider here the system here, or the control volume. What are the components of this system? And we want to calculate the power, we want to calculate the efficiency, and this is what we call the performance field. So it is similar, exactly similar to the previous chapter. The only difference here, it is this word. It was vapor power cycle, now it is gas power cycle. Okay, now do you know what is this? Shabab?
Combustion chamber.
Yeah, it is a combustion chamber. Where do you find this?
This thing that for gas.
It is in the automobiles, right?
Yes.
Yes.
This is what we call
Yes.
internal combustion engine. So what happens here is that the piston goes up and down and pushing here the crankshaft, and then it causes rotation here. So this is reciprocating inside the engine, and this is rotation that goes to the tires and moves the automobile. So this is what we're going to consider internal combustion engine. I just want you in general now to understand what happens here. You can see here, this is an inlet and this is an exit. So in the inlet here, you have fuel and air goes in, or fuel or air and then fuel. Anyway, so what we need here is what we call it charge in. Charge in, that fuel and air goes inside here. This is from the inlet valves. Then this is here compressed and then burned with a spark plug here, and then it exits as exhaust here. So if you take a minute here and follow what's going on. There's an intake while the piston is moving down, and then compression, then combustion, and then this opens to get the gases out. So this is here, while this is going down, the inlet valve opens, the charge goes inside. So I have fuel and air now. Then the compressor, the piston moves up and then compress the charge. Then we have a spark plug, and then it burns, pushing the piston down, giving us work, and then it goes back here, the valve opens and the charge goes in. So this is a cycle and this is repeated all the time. If you have a question, please stop me at any time. Actually, Mr. I think Ali Al-Hajji, I believe, he reminded me that the previous two classes were not recorded, so I'm making recording this time, inshallah. Okay, Ali? Okay, inshallah, so you'll be able to find it. If you don't find it, let me know again if there's something wrong. Okay, what do we want to learn from that here is that we are going to sketch the PV diagram, TS diagram, apply the energy, exergy balances, and determine the power, thermal efficiency, and what we call the mean effective pressure. So I have, this is a performance factor. I want to calculate the power. When you buy a car, you are interested in the power. So this is one of the performance factors. The second is you do not want to go to the gas station everywhere. So this is the thermal efficiency. And we will also define a new parameter here, which is mean effective pressure. All right, so this is again learning here. Of course, we will ask you to plot the TC diagram. And this is the engine here, or the space where the work is done. Okay. So now this is the learning objectives, what we need to do. Of course, this is what we call reciprocating engine, and it is used in automobiles, trucks, and buses. So you see this every day. I mean, this is part of your life, is a bus or a truck or a car. So I'm sure that it will be easy to learn this because you can see it in life around you. Okay. Now we are going to divide here to reciprocating engine to two types. Okay. Two types. One of them is that the cars that use gasoline, and this is most of us use these cars. The other one is using diesel. So this is two types here are commercially we call them gasoline, and we call them diesel engine, diesel car. Okay. So the first group we call it spark ignition engine. Spark ignition engine. What does this term mean? Spark ignition engine. In terms of English, how do you explain that? It is the engine in which the ignition is done by spark. This is just an English expression giving like that. So when you say spark ignition engine, means it is the engine that in which the ignition is by spark. What happens here then? We take here at the inlet here, there's a charge. Fuel is mixed with air. And therefore, at this point you have here, while the piston is going down, the charge goes in, so you have fuel and air here. Then the piston compresses this to a high pressure, and then at a certain point here, we have the spark. And this spark will cause the engine, will cause the high pressure. This will push the piston down, and this is where we get the working. Then this is why we call it a spark ignition engine. So I have a charge here. This is charge, we have to burn it. What do we mean we burn it? If I ask you, how do you make a fire? What do you need to make a fire? Can anyone answer me?
A fuel and a spark.
And
oxygen. Okay, very good. So you complemented each other. So you need fuel, you need air in which you have oxygen, and you said spark. I just want to go beyond that. I don't know, it does not have to be spark. What do I need here is to heat it to what we call self-ignition temperature. Sometimes you can find like in woods or so, sometimes then you find that it burns by itself. So you heard about some fires in California last month, and this was due to that the temperature is high and therefore it burns. Why does it burn here without any spark or anything? It burns because we raise the temperature to what we call self-ignition temperature. So as a matter of fact, it is, you have three of them: fuel, oxygen, and what we call self-ignition temperature. They should reach a temperature at which they burn. How do you get this temperature? In this case here, we have a spark. So this is here is, I have a fuel and air here. I want to increase the temperature here. To increase the temperature, in the spark ignition engine, we have a spark, and this spark will cause the fire, and this is what we need to do. So this is what we call here spark ignition engine, and this is the diesel engines that we have in our the gasoline engine in most of our cars. What's the other type here? The other type here is what's called compression ignition engine. Means that the ignition here occurs due to compression. Okay, so this is here when you compress, the temperature increases, and therefore, but you don't have to make a spark. So you compress it, such the temperature increases to reach the self-ignition temperature, therefore it burns. In this case here, what we inject here, what we have here is air, and we compress this air to a certain higher temperature. So I have air. Okay, let me go back to the previous one here, please. Okay, so at this point here, I have fuel and air, and both of them at lower temperatures than self-temperature. So what are we waiting for? We are waiting the spark here. Okay, but then in this case here, we enter air only. We do not enter fuel. We enter air only, and then we compress it to self-ignition temperature. So at this point, I have air and the temperature there. So I need the fuel. The fuel we inject it here. We call this is injector at this point. So this is the difference between spark ignition and diesel engine or fuel injection. In a spark ignition here, I have fuel and air, and then the temperature is lower than the self temperature. Then I have the spark plug to increase this temperature. As a matter of fact, we have to make this controlled combustion. Means that we burn one layer here, and then the next layer, the next. We don't burn it all together, otherwise this will be explosion and the engine will be cracked. So now this is the spark ignition engine. We have fuel and air, and then we have the spark to reach the self-ignition temperature. So this is the three elements: fuel and air, and do not burn. Why? Because no self-ignition temperature. Then we have the spark to add the third element, which is self-ignition temperature. In diesel engine, we have air only. We pass air only in the engine. So air will not burn. Then we compress it to reach the self-ignition temperature. So I have air at higher temperature. It will not burn. How do I control that? Then I add the fuel here. This is in the injector, fuel injector, and this fuel injector. So now I inject the fuel. As you inject a part of it, it will burn. So this is controlled combustion as well. So there's a difference between spark ignition and then compression ignition. And this is here is the engine here for the compression ignition engine. We add air only. We compress the air to a higher temperature, and then we add the fuel. When the fuel goes in, it will find the air and the self-ignition temperature, therefore it will burn. Okay, Shabab, you have the difference between both of this here. Of course, at the beginning of each chapter, I explain the background and the engineering part, the physics behind that. I don't want you to just have a cycle, plot the TS diagram and apply the equation. This is not my object. You are an engineer and you have to learn about this. And this is why I'm giving some time here to explain the background and the physics of the problem. What do you see in the field or in life around you? And therefore, I will ask you again to dig into, give us some animation, some explanation of this. So I want, first of all, I mean, how does the engine works, similar to the previous curve here. So I want to see some animations regarding this. This will be for a bonus. I need one to do that. Another one will have the difference between spark ignition and fuel ignition. I want to learn about this here, such that we know what we are talking about. All what we'll be doing in our class here is to present the cycle, to present this in a cycle. I'm coming to that, but I need now animations. I need to learn a lot more about what are the engine, how does it work, what's the spark ignition, what's the diesel ignition, what's fuel, turbocharged engine. You heard about turbocharging engine, and you have injection, fuel injection car, and then you have carburetor before. So all of this here, try to dig into that and try to give us some animations to help the students. And this will be for a bonus, of course. Okay, so some terminology about the engine here is that we have the engine here goes up and down. There is a limit here at the max top here, we call it top dead center. So the piston will be going up to this point. and it will go down up to this point. So we call this bottom dead center. The distance between this and that, it is stroke. We call it stroke. And then the diameter here, we call it bore or diameter. If I ask you here, what is the diameter of the engine? 1 meter, 1 millimeter? Can you give me a figure? What's the diameter of the engine?
10 millimeter.
10 millimeter?
In centimeters?
Yes, in centimeter. How much is this?
1, 2, 3.
10 maybe, or 10 to 20.
Okay, 10 centimeters, that's fine. In the gasoline engine, it is smaller, so we say 10 centimeter. In the diesel engine, it can be more than that. But this is around 10 centimeter, and this is also around 10 centimeter also. So this is the size of the cylinder. We have 4 cylinders, 6 cylinders, 8 cylinders, but each cylinder is like this in the engine. So this is the cylinder, this is the piston going up and down. So when it goes down, it is a stroke. When it goes up, it is a stroke. And then this is the diameter. So we call this top dead center. This is the maximum point that the center, the piston reaches. And this is the bottom dead center, the minimum point that we have. And we define here what we call compression ratio. We are going to give this here. Later on, I will define this, but it is known as the compression ratio. And I want to, every one of you, to get this value. What's the compression ratio? So either you go to your car and see the catalog and see what the compression ratio. If you do not, now go and buy a car. Not even, you do not have to buy the car, but imagine now you want to buy a car, choose the car, and then either you visit a shop and see, get the specifications. You will find the specification is compression ratio. Or imagine what you want to buy a car and then go to the internet and get this value. So next class, I'll ask every one of you what's the compression ratio. So you can get from internet, but get the compression ratio, what is the type of the car and the compression ratio. And then we will discuss this in our next class, because this is one of the main specifications in the automobile. This will be found in each car specification. Once you get the specification, you'll find what's known as the compression ratio. I'll define this later on. Okay, but I want you to understand all of this here. We have the cylinder, piston arrangement. This is the cylinder piston arrangement. We talked a lot about in thermodynamics 1. We annoyed you cylinder piston and cylinder piston arrangement. So this is the use of the cylinder piston. This is the cylinder and this is the piston. This is reciprocating in this direction. This is the diameter. And then I have the spark plug, valves in and valves out. And then we call this clearance volume. This is the clearance volume here. Clearance volume is that this is the space left here. When the piston goes all the way up, there's a space here, we call it clearance volume. Remember this clearance volume. And when we divide here the volume, the maximum volume over the clearance volume, this will give us the compression ratio. So the volume here from this point to this point, this is what we call the total volume, the maximum volume we reach. And then this is the clearance volume. The maximum volume we reach here divided by the clearance volume, this is what we call the compression ratio. This is a very important specification. We'll find later on that the efficiency is a function of this value. Therefore, when you go buy a car, you want higher efficiency, look for higher value for R. This is one of the things that you should look for. All right, this comes down here and rotates this direction, and this goes to the tires, and then the car moves. Is everyone clear how the car works now?
Yes.
Yes.
But I need you to practice that. I mean, whenever you see an engine open, look at what happened there, and then also animations. I will get so many animation from you, inshallah. Okay, now we'll go more of how the engine works. Okay, so now what we call here, first of all, okay, I'm putting this here, but it's not animated, but this is what happens here. The engine, let me go back here. This is the start position here. Okay, so it starts from here. So the piston at this point here, this is the point here. Then this valve opens and the piston goes in this direction. So this is, I'm going to repeat it again. The piston at this location here, okay, and the piston moves in this direction. When it moves, the pressure here is smaller, will be lower, and therefore this is open, so the fuel and air will go in. So in this here, this is what we call intake. Intake means that in this the piston is moving in this direction, and then the pressure is less than the atmosphere, and therefore the fuel and the air will go inside. Okay, this is what we call the intake, the first stroke. This is each movement from here to there, it is what we call a stroke. This is the amount here from this point to this point, we call it stroke. Okay, and then we have, so the piston first moves from here to there with the valve open, then it takes the charge here. So now I have a charge of fuel and air in the spark ignition engine. Then what happens next is that the piston, the compression, what we call the compression stroke here. Then what happens here is that we have this moves here up, the piston goes back here. And while this valve is closed now, so now the valve is open here, then it takes a charge and then close. خلاص. The charge here is within the cylinder now, and the valves are closed. And when the piston moves in this direction back here, what happens? This is a compression now. The pressure, the volume here will be compressed, and of course the pressure will increase, the temperature will increase up to a certain point here. All right, so now you understand the intake, and then the compression, what we call intake stroke, compression stroke. Then we have here, of course, is defining here between compression. Repeat this again with compression and the spark ignition. Then we the difference between spark ignition, compression ignition is that we have in this point, if this is the spark ignition, the gasoline engine, you have a mixture here. In the compression ignition, the diesel engine, you have only air here. So the only difference here is the charge. So at this point, now we have intake. In the spark ignition engine, we have fuel plus air. In the compression ignition engine, we have only air. Then the valve is closed here, the piston moves back, and then this is the charge here. I'm calling it charge. It can be fuel and air in the spark ignition, or it is air only in the compression ignition. It is compressed here, reaching certain point at this point here. All right. Shabab, we understand these two strokes. Intake, which you suction, what we call suction stroke, that means that you take the charge in. Okay. Then this is compressed here up to this point. Okay. Then the third is what's called power stroke. Okay. Now we have the spark. What happens from when you do the spark? Let me build this again. What happens if you have a spark here? What happens? It will burn the fuel and the air, and then you will find high pressure and temperature. The pressure increases, and this will push the piston back to this position here and giving us power. This is what we call it power stroke. At the end of the power stroke, then the piston will be at this position here. Then the piston moves in this direction and pushing the gases out. So this is what we call here the exhaust stroke. So this is, let us repeat this again. One stroke here to take the charge, another stroke to compress it, and another stroke. What happens here? You have the spark plug, or you inject the fuel. So you have a combustion, high pressure, and this pushes the piston in the back here, giving us power. And then you open the valve, you open the exhaust valve, and then the piston moves in this direction, giving the exhaust out, and then it takes another cycle and so on. So this is the actual cycle for the internal combustion engine. This is the real cycle. When you have the pressure, when you have at this point, you measure the pressure and volume, you will get this here PV diagram, and we can do this in the lab, and then we get this is what is the cycle here. So this is the first thing you want to understand, how this works here. And what is our objective here? Our objective in this chapter is to calculate the work here. I want to calculate the power, and then I see how much fuel we added here, and then we calculate the efficiency of that. Okay, so this is we will come to that. But let's do one thing here. How many strokes we have here? Stroke, as I mentioned, here is the movement from this position to this position, or vice versa. How many strokes?
4.
4 strokes. So this one stroke, second stroke, third stroke, fourth stroke. So this is what we call it. Why we call it here 4-stroke engine. 4-stroke means that the cycle occurs in 4 strokes. Okay, how many revolutions here in the cycle? In this cycle here, we have 4 strokes as we mentioned. How many? 2 revolutions. Yes?
Two.
Question, or you're saying 2 revolution?
Yeah, I'm saying 2 strokes.
Okay.
2 revolutions.
So it is 2 revolutions here. Why? Because when the piston moves here, the crankshaft will move from this point to this point. Then when it goes back, it will move from this point to this. So this is 1 revolution here is 2 strokes. So we have 4 stroke, 2 revolutions, 1 cycle. So every 1 cycle has 2 revolutions the crankshaft and has 4 strokes. All right. Okay, now this is what I called here is the compression ratio. It is the V maximum, which is this volume, all the volume here. This is the maximum volume divided by what's called here the clearance volume. This is what defines the compression ratio. So I want you to remember this here. This is the compression ratio. Is this total volume divided by the clearance volume, which gives the R here. R is very important. Next class, every one of you will give me a number, a value for the compression ratio. All right. Now, how can we calculate this work here? And this is our study here is that how to simplify this for you students and ME204, and then such that we will be able to calculate the power, the net power here. So the net power here is this part minus this part. Why? Because this is positive and this is negative here. Okay. So we want to calculate this here. And therefore, we are going to simplify this, okay, such that we will be able to calculate the power in this case. So now what we are going to do is the following. We are going to simplify this to that one here. Okay. First of all, this is what we call pumping work. And you'll find that this is the difference here between, this is the atmospheric pressure. To have intake here, then you have to lower the pressure such that the charge will go in. Anyway, so this is very small and we are going to neglect this amount of work. Means that the intake and exhaust will be at the same pressure, so I'm not going to show them here. And then we have this part here. This part we are going to, I cannot integrate this here and it will be complicated here. So we want to consider a cycle, a certain processes that we know, isentropic process, constant volume process, isentropic process, and so on, such that we can present this in our class here and we calculate the power. So we're going to approximate this here to this cycle here. Then we have this as isentropic. This is almost vertical, so we can say this is a vertical line, and then this is another isentropic. We can say that this is isentropic. This is the approximation here that we can do. So to calculate the work, similar to when we have certain data, you say I'm going to approximate this as a straight line, and this is what we are going to do here. As we mentioned here, our objective is to calculate the power, calculate the efficiency, and there's another parameter here what we call is the mean effective pressure. Mean effective pressure is W net over the volume here that we have. Okay, I want to ask you here, so this is the total volume, this is the clearance volume, and this is what we call the swept volume. Why we call it the swept volume? Because the piston goes from here to there, so this we call the swept volume. If I ask you here, in the engine, in each car, they write a number there, 1.4, 3.5. What is this number written on each car almost?
The stroke volume.
The stroke volume, okay. So this is an expression. It is what we call here the swept volume. Sweep means that you sweep. Sweep in Arabic means yaksah, means that you push the fluid from it. So the volume of this region here is what we call the swept volume. It's coming from sweep, which is done through the stroke here. So when you say 3.5 engine, 3.5 what? This 3.5 liters, right?
Yes.
Okay.
Yes.
So this is here is the size of that. So when you read 3.5, means that the engine you have is this is the volume of the one cylinder multiplied by the number of cylinders. This will give you this. This is the volume there. So this is the volume. It's not the total volume. It's not the clearance volume. So the volume between this point and this point. This is what we call the sweep volume and the swept volume, and this what's given in the car, and this will present how much power this car with that. So W net over the swept volume, which is V maximum, minus V minimum, which is this one, the clearance volume, this will be called mean effective pressure. And this is another parameter here that we use to evaluate the car. For example, I ask you about 8-cylinder cars. Is it more powerful than 4-cylinder cars? Definitely will tell me yes. It has more power than the 4-cylinder car. So now how can I compare between the performance of both of them? So I divide here by the swept volume. So now I remove the point of 8-cylinder or 4-cylinder. So I divide it by the volume. If the volume has the same, if both has the same volume, what will be the power? So this is why we are considering the mean effective pressure. So in the question now, I ask you in this chapter, what is the question? Calculate the net power, calculate the efficiency, and calculate the mean effective pressure. So you know the problem now. You know the problem which will have in any exam. What is the power? What is the efficiency? And what's the mean effective pressure? So this is the three elements which we call the performance figure, similar to your GPA experience. Something like this will be your grade in senior design project or something like that. It's less important, but it is also important. It is also a performance figure. All right. So now we have. Okay, let me make some practice with you now. Okay. Can I ask you calculate the time for each cycle? How long each cycle takes? 1 second, 1 minute, 1 hour, or what?
Smaller than a second.
Smaller than a second, but now that's good. But how, can you calculate it or not?
Yes, it's written revolution per minute.
All right, very good. So this is here the revolution per minute. Revolution per minute, if you reverse it, will be minutes per revolution, right? So if you say 1 over 2,000, it's almost around 2,000 to 2,000 to 3,000. So if you say 1 over 2,000, what does this mean? It is how minutes taken for each revolution, right?
Yes.
So 1 over 2,000, this is here is the minutes per revolution. Because I need 2 revolutions, so each cycle, so I divide this by 2. So now this is here is how many minutes per cycle. Then I multiply by 60, this will give me the minutes. I multiply by 1,000, this will give me the millisecond. So I want you to multiply this here. One can do that, and then this will give me the time taken for each cycle in milliseconds. So this is 30 milliseconds or something like that. So this is a figure that you can calculate for your car. I did not get anything from mine here. This is the revolution per time per minute, and then you can see, you can calculate from this the time of the cycle, and then of course you can get the time of the stroke and so on. So I want you to have exercise this so you have more feeling, more depth feeling of the engine. All right. Okay. So this is the mean effective pressure, as we mentioned here. We call it net power. The net power when you calculate the power, and then divided by the displacement volume. This is the displacement volume which you find in written in each car. And this, of course, this value here will increase the cost. When the displacement volume 3.5 cylinder is more, of course, in cost than 2.5, than 1.2, and so on. All right. All right. Now what we need to do here is to go to the simplifications for the cycle. Okay. Let me go to what we call now air standard cycle. Air standard analysis of the cycle. This is the assumption that we make such that we can simplify the cycle. I want to calculate the power from the previous diagrams that we have, and we cannot integrate this area, so therefore we want to calculate to make it simple. To simplify it, we are going to say there is no valve flow in and flow out. It will be a fixed mass of air, and this can be considered an ideal gas. So in 2.4 in this part here, we are simplifying your life now is that this will be considered an ideal gas. You can say PV equals RT and all of that here. This was forbidden in the previous chapter. Now you can apply that. And the combustion process, because in this stage we do not want to burden you with the combustion process and fuel and the air. It is too much for 200 level, and therefore we are going to replace the combustion process by heat addition. And then we are going to remove the intake, and then also since this is closed system here, we are going to say here that there is no intake, there is no exhaust. With this here, we are going to, we'll call this cold air standard cycle, means that there is no fuel, there is no combustion, and so on. So this is to simplify that, and Otto is the scientist who has done this cycle. So now we are going to study Otto cycle. So let me say, what's Otto cycle now? Otto cycle is a simplified cycle for the actual engine. So I'm taking you from the actual engine to the Otto cycle, and this is what I'm going to explain to that. So Otto cycle will be the cycle for gasoline engine, which is spark ignition engine, and diesel cycle, which will be for diesel engine. Okay, we'll come into more details about that. So these are the cycles that we're going to use: dual Otto cycle, diesel cycle, and dual cycle. Similar to reheat cycle, regeneration cycle, we are going to have 3 of them here. But let me now go to the cycle here, and this is a little bit simplified. So we removed the intake and exhaust here, we removed 2 strokes, and now this remains here. We want to even to simplify this here. So now we are going to this one here. I'm putting here the cycle. Okay, so now we remove this part. All right, so we mentioned that this pressure is close to that pressure, so I'm going to consider this as a line here. So there's no intake, there's no exhaust, but the cylinder has some air inside. This is compressed and expanded. Okay, so now we remove this one. And then I want to approximate this here. So I want to put some processes here that I can calculate. So now I'm going here, and then I start from here again. This is the starting point, which is this one here. We are going to consider this process as isentropic process. You can see this as isentropic process here. So we are going to approximate this as an isentropic process. Okay, it is similar to what you have in physics. You have certain pieces of points here, and then you want to make a line here, and therefore the line goes inside of that, and then you approximate this as an isentropic process here. Why I'm making this isentropic? It is approximation of that, and therefore isentropic process, I can calculate the work from that. If I know isentropic process, then I can find this work. Then Otto mentioned that this is almost vertical. Approximate this as a vertical process. So it's going to approximate this as a vertical process here. So this is constant volume process. So I can calculate the work of that, the heat. So it is, you know that the work is equal to integral of PdV, because now this is a system, a closed system. So now with this here, I can calculate the work under this and the work under this. Then I'm going to approximate this also as a constant entropy process. And then I can approximate this as, again here, constant volume process. So this is the cycle, Otto cycle, approximating this. And this is what we call a genius person, is simplifies life, not complicated. Okay, so when you complicate, so Einstein mentioned something like that a genius person is to simplify things, not to complicate. So this is I want to calculate the area here. How to calculate the area here? This is drawn by the engine in the lab. We can get this back. But now I want to calculate that, so we simplify it here to isentropic process, this one. Then this is approximately constant volume. This is approximately constant entropy. And then we have this one. So now this cycle here turns now to this side. So this is the actual life cycle. Okay, this is what we see in the field. When you come to the class, we are going to simplify to this here, and we are going to analyze this side. So I have 4 processes now here. One of them is compression process, isentropic, from 1 to 2. Then we add the heat here because we are replacing the spark here and the fuel added here by heat addition. So we have heat addition from 2 to 3. Then isentropic process, then 4 to 1. In the TC diagram, it is isentropic, constant volume, isentropic, constant volume. And this is a cycle, so your responsibility, first responsibility, is you understand how the actual cycle, how the actual engine works. Then how to simplify it to a PV diagram and how to plot the TC diagram. This is your second responsibility. Then after that, we want to calculate the work here, which is the area under this, within this diagram here, 1, 2, 3, 4. This will be W net. And then we calculate heat addition is the area under 2 to 3, which is P23A. So we calculate this area, then we calculate the efficiency. And then we divide W net over the swept volume here, and then we calculate the mean effective pressure. Okay, are you up with us here? Is that where do we start? How we have an engine running in the street, and then how do we analyze it here in the class, and then we go to the analysis here, and this is our objective here. All right, Shabab. So this is Otto, what we call Otto cycle. Otto is a scientist. What did he do? You can do that. I mean, you can have Fahd cycle, Faisal cycle, Alif cycle. You can do your own. So all what he did is that he found that this is a cycle here, and he simplified this into this cycle here, approximating this cycle to that. I know it will not give you the exact value here, but whatever happens when I optimize the cycle, try to improve the power, try to improve the efficiency, all of this qualitatively, it will apply to the same cycle here. So I can improve the cycle, it will also improve that here, because this is simulating that. But I can say here that efficiency will not be exactly the same, but this is the way. So all what Otto has done is approximated the cycle into different processes that I can use to calculate the power and efficiency. All right, so this is what we are going to start. So now we are going to move from the field. Alas, we are not in the street now, we are in the class, and we want to calculate the power and the efficiency of the cycle. Okay. So now we have again the compression ratio. You will get this value next time. R is V1, which is the volume here, which is this V1, divided by volume V2. So this is here is the clearance volume, and this is the total volume of the cylinder. And between A and B, this is the swept volume, which you can see on each car, the value of that. All right. So R here is the compression ratio V1 over V2. Next class, everyone, I will ask him what is the compression ratio, which car, and what's the compression ratio. All right, so what we are going now to consider is what is known as the air standard cycle. Air standard cycle is Otto cycling. And this is simple analysis here. We can, what is W12 here? Because this is isentropic, so there's no heat transfer. So Q minus W is equal to U2 minus U1. You remember this from thermodynamics 1. Q minus W is equal to U2 minus U1 because this is so Q is 0. So now I can calculate W1 to 2 is U2 minus U1. The same here, W34 is an isentropic, so this will be U3 minus U4. And the amount of heat added, we add the heat here. This Q minus W is equal to U3 minus U2. Where is W here? What is W from 2 to 3? What is W from 2 to 3?
0, 0, 0.
0 because this is integral of PDV. So the work here is 0. The area under this is 0. And then we have Q rejected here. It is U4 minus U1. So we can calculate that. So now we can calculate W. W, this is the compression. So this is the compression work. And this is the expansion work. And the difference between this here will give me this area, which is the network. And therefore, I can say the efficiency is U3 minus U2. I can say also Q minus QH minus QL over QH. So this is QL minus this QH, which is U3 minus U2, minus QL, Q4 minus U1, and then over U3 minus U2. Or I can say 1 minus QL over QH, and this will give me the efficiency of the cycle. So now we calculated, now we started from a real engine, we simplified to a simple cycle, which is done by Otto, and therefore now we can calculate the work and the efficiency. This will be what we are going to do, to ask you to do. Then we sometimes do approximation here because this is a gas. We can consider this as an ideal gas, and if I assume specific heat is constant, so I say CV multiplied by T4 minus T1 and CV multiplied by T3 minus T2, and therefore we can calculate the efficiency based on temperature. All right, so this is what we call air standard cycle, and this is here is the heat addition. It is the area. It's an explanation of this here, and then this is the heat QL. So this is QH, this is QL, and the difference between of the both of them will be the net power out. So this is W net here is QH minus QL, and then we have this is W net. All right. So now we have in PV diagram, this is the compression work, this is the expansion work, and therefore, then the difference between this is the net power output here. So now we understand how to get that, and we understand how to calculate it. One thing I wanted to say here that as you increase the compression ratio, you see here that we are improving the power and also the efficiency. Improving the power, you can see the area is increasing. What I have done here, instead of 2, I increase the compression ratio here, then it reaches 2 dash. And then, therefore, we have increased the power and we have improved the efficiency. Why improve the efficiency? Because TH has increased here. And this is why I'm saying here that R is a very important figure here in that. And whoever will find R is more, then the efficiency is more. And therefore, we can plot a curve here, and this curve will tell us here that the compression ratio R is increases and the efficiency is increased. Now I want just to get some of you, I know most of you will go and get the gasoline engine because this is available in the market. But I need 2 students will get R for compression for diesel engine. Okay, can I have 2 of you volunteers who do not have a car now and they want to buy a car, and I'm asking them to buy a diesel engine car. So I need 2 of you, to get R for a compression ignition engine. I have a purpose for that. Okay, so everyone will get R. I need 2 volunteers now who are going to get a diesel engine R. Okay.
Yes, I can get.
Okay, so I have 2 now. We'll get R for a diesel engine. The rest can do, but I need some of you for gasoline and some of you to get for diesel engine because I want to compare between them. I have an example here. I will go quickly through. I have still 4 minutes. I'll go through that. So this is the example here. Is an Otto cycle having pressure and temperature. So we are given pressure and temperature at the inlet. Why we normally have this here? Because we get the air from atmosphere. So these are normally the atmospheric condition here. So I may give you a problem without P1 and T1. Why? Because this is the atmospheric condition. Here you can get that. And this is the volume. And then we are given here the heat addition here. Anyway, I want to explain the process here. Normally T1 will be given because this is atmospheric condition. And then we have, this is the compression ratio, V1 over V2. And therefore I can calculate T2 from that. So T1 multiplied by R to the K minus 1 to get T2. I will explain this example quickly in 2 minutes. And then I leave it for you to read at home. And then next class, I'm going to repeat this again. So this is the process here, how to get the temperature. So I can get T2 here at this. Then I can also calculate the volume. The volume will be the ratio of PV to the K equal to constant. I have this is given. I have P1, so I can get P2. Then Qn either I calculate it or it is given. In this problem, it is given, so I can calculate T3. Or I give you T3, then you can calculate Q. So either one of them will be missing. So now we can calculate here to get the specific volume. We get M over V1 over V, and therefore I can get the specific volume like that. And then I can calculate Qn because it is given in the problem. This problem Qn is given, so I can calculate Q per kilogram. Then I utilize this equation here. As I mentioned, in this problem, Q is given, so I can get T3. And in another problem, I will give you T3, then you calculate Qn. So anyway, either one of them, you can calculate the other. And then we have T4, we can apply the same equation. This is the value for R, then calculate T4, and then also calculate T4, so we can get all the properties. Once I can calculate Q out as CV delta T. With this here, I calculate W net, and then I calculate the efficiency and mean effective pressure and back work ratio. Sorry, I'm talking this fast here, but I will repeat it next class. But I ask you to read this from the notes, and then we will come back to read it, to solve it again. Okay, so I'll stop at this point. I think you have a couple of questions. Hassan mentioned to me that what covers in the exam we have. Okay, let me take attendance first. So if you have to leave, then you can leave. I'm taking the attendance now. I forgot to take it at the beginning. Anyway, okay. So I took attendance, and for Ali Al Hijji, It is being recorded as I see it recording. So please, Ali will let me know if it is well recorded or not. And every class at the beginning, you can remind me if it is. You can see it's recording, right, or not?
Let me check it.
Yes, we can.
Yes.
It is recorded. So if you do not see I'm recording, just remind me at the beginning of the class. So I push the button here to be recorded. So the exam will be. We have an exam on October 26th. All the exams will be, all the sections will be in the same time. However, will be different problems. And also I practice with you, here's the different problems. As a matter of fact, I don't like to go with camera and all of this business. I want to concentrate on learning more than watching students cheating and so on. But I do my best here to make it different exams. It is a headache on myself. As a matter of fact, I'm solving around 15 or 20 problems. For when I made the previous exam, I had to solve it 20 times with different exams. So I will follow with that rather than bothering you with the camera or something like that. But we will have on October 26th. I will discuss with you the time. Hassan, can you see which is the best time for us? Probably after Isha, so maybe we'll start at 8. It will be for 1.5 hours. So Hassan will update this with me, inshallah, and then we'll transfer to you. Then one asked about the little grades. It will be better than what's given in the registrar. The registrar says A plus is 95, A is 90. We will do it better than that. So we'll be relaxing this a little bit. All right. So, but this is the maximum we will reach. Okay. Any other questions so far?
الدكتور الماتيريال
Material chapter 8 and chapter 9, which is vapor power cycle and gas power cycle. But the exergy, we will embed it in that. So I may ask you what is the reversibility, calculate the reversibility, calculate the exergy at a point. So I'm not giving a problem exactly on exergy, but parts of the problem, part D or E, will be calculate the reversibility, calculate. So part of it will be on chapter 7. So the coverage is 7, 8, and 9, as a matter of fact. But the problems will be from 8 and 9, and chapter 7 will be parts in the exam. Bakr, I wanted, before I forget, Bakr, I didn't need to get the figure for the PV, for the efficiency versus the pressure. Can you send it to me, huh?
Yes, I will send it to the group right now.
Yeah, please send to the groups. I want to see it. And I'm sure that you have a nice figure now with some scattered, some students solve it wrong, so exclude this.
So, Doctor, in chapter 7, we include just the exergy tablets.
We exergy I can, for example, ask you at the inlet of the boiler, calculate the exergy. So this is coming in. So in the problem for regeneration, for example, at the inlet of the turbine, I ask you to calculate the exergy at state 1. Then I include chapter 7. I say in the turbine, calculate the irreversibility in the turbine. So you have inlet and exit, so you do that. All right, so it will be part of the question.
So, Doctor, from chapter 7, just we have to study that exergy and reversibility.
Yeah, which is all the chapter then, huh? Yeah. It is always, but I'm not going to get a problem specifically on that.
Okay, Doctor, out the question, how many questions in the exam?
Three questions. Every one is half an hour. So you have regenerative, reheat, you have auto cycle, diesel cycle. Still we have time. I mean, we are going to have to finalize this chapter before the exam. So it will be 3 problems. Most likely 1 from chapter 8 and 2 from chapter 9. But I will update you later on, all right? I didn't write anything yet. It's in 26. Still we have 3 weeks, huh? Any other concerns, Shemab? Regarding the project, I already uploaded the project, and all of us will use the figure which will Bakr send it to us, and then calculate as I gave it to you, calculate the economy and calculate the effect on the environment. And once you finish this, you can submit it on the blackboard. And I don't want to discuss everything with your fellows, but once you write the report, nobody should see it. If I find any tools, this will be reported to the administration. Okay, please go ahead. Questions?
So,
Doctor,
Doctor,
Shall we leave, Doctor?
Yeah, if you want to leave, you can leave now. If you want to ask, I'm staying with you.